Okay, so I will start today by this technical presentation. My name is Shawn Gao, and I work for MTS. So the title of this presentation will be an overview of the real-time hybrid simulation techniques, which is the theme of this morning's topics. Real-time hybrid simulation solution. First, I will talk to you about the MTS solution. Shawn, you already mentioned some of them. It's kind of like a review for you guys, probably. And the main part for my talk for this session will be actually a dynamical stability analysis for a real-time hybrid system. So I will first talk about single degree freedom structure dynamic problem, then try to expand that to a multiple degree freedom system, then use a couple of demo examples to show you why we are doing that and to get a better understanding about it. And a third subtopic will be using a reduced order model to do real-time hybrid simulation. And then I will give you a summary about the talk. Though this is just the motivation page, you already see it yesterday, so why do we want to do real-time hybrid simulation on top of the techniques we already have for quasi-static hybrid simulation, right? The reason being that the physical testing specimen could be strongly mass, have a strong mass, or large damping. So when you are testing those type of systems, you have to do a dynamic real-time testing in order to get a realistic response. If you artificially slow it down, then you don't get nothing that makes sense from this testing. And of course, when you do real-time hybrid simulation, you will need to upgrade the hardware to do so, like a high-force dynamic actuator comparable to some of the the static actuator versions. And the pumping system, you need to have a larger pump in order to make the motion. And in terms of software or the algorithm side, the control method and the system modeling are actually currently being actively developed by the academic world as well as in MTS, because that's where the challenges are, and you need to have a very strong algorithm to overcome those challenges. I'm going to talk about it later actually in my presentation. So this is just a flow chart you already seen before, I guess. So this real-time target PC, which you already saw also in the demo room yesterday, that's where we can program some algorithm to make your numerical analysis execution in real time. And then, of course, we need to have our MTS servo controller, which does all the inner loop servo hydraulic actuation control. Both of those two machines are real-time machines, and they are connected through this reflecting memory technique so that they can be pretty much synchronized with the minimum latency. So according to the ScramNet specification, they can do data transfer in the order of microseconds. So that's pretty much, you can think of those two real-time machines are like they work at the same time. So every data show up on one machine will immediately be reflected to another, and then vice versa. So we use this quite a lot in our real-time applications. For example, if you have even multiple stations, all of them are real-time machines, then they are shared memory, they are all connected by the ScramNet card. Then I borrowed this slide from one of my colleagues. So this basically shows the idea. This is ScramNet shared memory ring. It's a network of shared memory machines. All of them are doing real-time operations. Then on any of the machine, when you have a data you want to send over to the ring, it will show up there immediately, instantaneously. So that's when you have a very large and complicated test setup. This reflective memory helps you to keep up the real-time constraints of your system. So that's just a quick overview, and then I'm going to do this a little, this is a little bit technical about dynamical system and stability analysis of a real-time hybrid system. So we know that any realistic control system like our actuators, or you can think any motion control devices, when you look at the behavior of it, it always has some kind of amplitude roll-off and phase lag, especially when you go to higher frequency, you will see more significant. In the time domain, you will see this phase lag, right? We already talked about it yesterday. So because of this phase lag, it will introduce negative damping into your hybrid system. And this is detrimental, this negative damping, because it can make your system go unstable. So the goal for me, actually, through the next couple of slides is we want to quantify this negative damping. So we want to know, so if I have certain delay in my actuator control, what's that negative damping added into there? So that, we want to know the system level response of your real-time hybrid system. So to do that, I have to use some equations. I cannot think of another way, but I promise you it's just simple, structure dynamic equation, nothing more than that. So if you can focus a little bit, we know that for reference structure dynamic problem, we have a second order differential equation, mass, damping and stiffness. So, but when we do hybrid simulation, we have to divide this into two portions. The N subscript denotes the numerical substructure, and the E is the experimental substructure, right? We can divide those MCK arbitrarily into two parts. But because we have this control error, meaning that your actuator is not a realistic device, we know there will be amplitude and phase control error in there. So we write out it into this form. Now this XE subscript experimental, it's not going to be exactly the same as the reference structure response X, right? Now they are in different state. One may be lagging the other a little bit, or maybe leading. Yesterday we showed that, Andreas showed that in the demo too. But the lagging one is actually the more detrimental one. So go a little bit further. We assume that your structure reference response is at this sinusoidal mode. It's the omega is the natural frequency of your system. So it's predominantly that's the response of that. And then we said this XE is going to have some error. So this capital dirt is the amplitude error. This small dirt T is the phase error, right? So now they are different. That's the challenge we need to overcome. And we do a little trick doing some linear approximation. Then we can write out this XE as a function of X and X dot. Similarly, we expand the velocity and acceleration terms. Now everything is in the state of X. And then we plug this guy back into the equation of motion, and we come up with the equation of motion for a hybrid system. So now we come up with this equation of motion, we can do a little bit observation. First of all, this is where you see this negative damping is, right? It's minus KE. So that's the negative damping we are talking about. And if it's too large, then your system will be unstable. Another important note I want to say is here, this negative damping depends on two different things. One thing, of course, is this control error, right? This delta T and the delta, they are the control error. But there is another part, which is the product of that, it doesn't depend on the control error. It actually depends on how you do your substructure partition, how you divide your mass, stiffness, and damping between numerical and the physical part and experimental part. So this thing, sometimes we don't really think it in that way, but we know that it actually plays a very important role. I will show you in this same equation of motion. I'm going to show you a couple cases. For example, this special case 1, we think about that we have a numerical substructure which is huge, high-rise building, a lot of mass, a lot of stiffness in there, but we are testing on only a very small component physically. When we do that, because your numerical substructure is going to dominate the whole hybrid system response, so even though you may have a bunch of control errors, your real-time hybrid system will be very easy to deal with. Your system response will be very close to the reference response. And the special case one is a little bit more interesting. For example, we can actually make this term goes to 0, right? We can divide the substructure in a way that this coefficient term goes to 0. Then even if we have a large, huge control error, this is not going to introduce much negative damping into our system. So it's not critical. You know, control error in this case is not so critical, but of course it's not something we really do realistically. It's just a concept, you know. And the third case, I call it the worst case partition. What does that mean? Meaning that if we have a single degree freedom dynamic problem, we divide our substructure in this way so that the whole frame, the whole stiffness is being tested physically, experimentally, and then the seismic mass is assumed numerically. In this way, this KE becomes very large, and then your negative damping, even if you have a very small control error, you are injecting a large negative damping into your system. And then this ME term is negligible because pretty much all the seismic mass is assumed numerically. So this is not going to counterbalance any of that negative damping. So in this case, even a very small control error could make your system go unstable. Unfortunately, this is one of the most very widely used test configuration in the quasi-static world, right? A lot of times we build the structure system, that's our interest. We want to do a testing on it, then yeah, we don't need to construct a huge seismic mass on top of that structure. That's the merit of hybrid simulation. We can just simply assume the mass because it's easy to assume a mass. But when you do real-time hybrid simulation on this type of configuration, you need to be careful about it. It's very sensitive to the control error. So to give you an idea, this is a plot showing you the maximum allowable control phase error that delay you can tolerate in a real-time hybrid simulation. So for example, when you have this system at the natural frequency, if it's 1 Hertz, then you can tolerate about 6.5 milliseconds of delay. That's something, yeah, okay, I think we can do that pretty much. But when your structure natural frequency is about 5 or 6 Hertz, then the delay needs really to be under 1 millisecond so that your system doesn't go unstable. That poses a lot of challenge now. 1 millisecond is actually our controller clock. So you have to beat up that controller clock. You can pretty much get a perfect control in order to make this real-time hybrid system just to make it stable, not to mention performance, right? So I think that's my, I hope you can get that concept. So first, when you design your real-time hybrid system, do the, substructure partition, think about, how you want to divide your substructure. Don't get into somewhere you have to, go to this region, then, you have to get an extremely accurate control, and that's challenge, very much, very, very challenge. Go to multiple degree freedom, of course, all realistic problem is a multiple degree freedom. So same equation of motion, but of course everything now is in matrix form and is in vector form, right? And the little trick we do here is that we want to solve the dynamic equation of motion in the model coordinates, in the Q. You assuming classical damping, then we can decouple the modes in the first mode, second mode until the nth mode, if you have n degree freedom. Then of course we can get the natural, x as a function of Q is just the model matrix. That's just the structure dynamics. And once we do hybrid system on a multiple degree freedom system, again, so we said no, okay, now we will have introduced some kind of control error. So this control error can be also expressed in the state of Q. It's the amplitude and phase error. Of course, now each individual mode could have a different error in there. But at the end of the day, it's a similar concept as in the single degree freedom. We use some linear approximation, we get this expression, Now everything in the state of Q, plug back to our equation of motion. That's our new system equation of motion. Convert it back from Q to X space. Then eventually you see this. Now it becomes a little bit involved, a lot of matrix in there. That's your equation of motion for your hybrid system. So, for a simple structure dynamics problem, MCK matrix, but now it becomes a lot of matrix. So, similarly, we observe here, that's the negative damping term actually there. So, that's where, this term will be actually the most, challenging one you have to deal with, at least to maintain the stability of your system. So eventually, why do we want to construct this equation of motion? Because that represents your hybrid system response. Once you have this system equation of motion, you can do whatever you want. You do frequency domain analysis, you do time domain history analysis, you can do anything. So let's show this as an example. For example, this is a 3-story prototype structure, and these 3 floors, they are both supported by brace system in both directions. It's actually a very stiff structure. So this is actually a realistic structure that is being tested in one of the universities in China. And their idea first was that they have this tested on their shake table. And then they want to say, okay, if my hybrid simulation response can be compared to the shake table response directly. So they did the shake table test, and then once they decided to do the hybrid approach, so the first proposal we had was thinking, okay, naturally you have already your frame structure system already constructed, it's sitting there, everything is built. We can just attach 3 actuators on each floor, and then again, we just assume those seismic mass numerically, and then makes your hybrid system. But that actually got into this worst-case substructure partition. For the static talking, it's easy to, it's straightforward. I'm not saying it's easy. Conceptually, at least, it's straightforward to do this type of hybrid simulation. But when you go to the real time, that's what we end up to be. For example, that's their design case. This is a frequency response function before we do hybrid. This is just a reference system, right? 3 modes, 7 hertz, 20 hertz. The third mode is actually about 34 hertz. So same, the system zeros, the poles are actually here, 3 sets of poles. The 3 modes represent 3 modes. They are all stable on the left side of the coordinate system, on the left side, meaning that your system response will be decay with respect to time. That's the purpose of the damping. But once we do a hybrid configuration and using the equation of motion we just saw a couple of slides back, construct that system, do the frequency response plot, and the system post, you can see that now it's actually an unstable system when I just only introduce 1 millisecond of delay. So the first mode is still stable, although you can notice it shifted to the right half plane. It added negative damping in there. The second and third mode, they are already on the right hand of the plane, so that your response will go exponentially with respect to time. It's pretty much unstable. It's going to blow up. Whenever you click the button to run the test, it will go up, blow up. So then I told them, that's too challenging to deal with. You have 3 actuators, they are fighting each other dynamically. The specimen is very stiff. You want to achieve this control accuracy on all 3 actuators up to this high frequency? No way. That's just too challenging. And then we said, okay, what's possible if we modify our hybrid system a little bit? Design case B. Now I need to first lower my modes significantly by adding a lot of seismic mass numerically, of course. That's the easy way to do it. Same physical specimen over there. So now if I lower my mode to be 1, 3, and 5 hertz, And then I started to see how sensitive is this configuration with respect to delay. So 1 millisecond of delay, see, okay, we did introduce some negative damping on all modes, but they are all stable at least. Looks like it's possible to make it work under this 1 millisecond. And then goes up to 3 milliseconds, you see that mode actually started to go a little bit like marginally unstable. It's shifting very close to the right half plane. So it's becoming a critical point here. And if you go 4 milliseconds, if you add a little more delay in there, you see actually the system go unstable. So 3 to 4 milliseconds is probably somewhere we can work with. 1 millisecond definitely too challenging. So then we did a virtual test validation about that, because the previous frequency domain analysis were all based on that equation of motion we just saw, we derived there. And now we do a virtual testing. Now everything else is the same as the real testing, only that, of course, we are just simulating this structure frame by a simplified 3x3 matrix, right? That's the global stiffness matrix. And then we can take a look. Design case B is the response I'm plotting here, because design case A, it automatically goes unstable with minimum delay assumed in there. So this is the reference response of the first floor. It's built based on the 3D OpenSys FEA analysis. No hybrid whatsoever, it's just pure analysis. Once we do assume a 1 millisecond delay in the real-time hybrid simulation, so you see that, okay, the response started to do some damping, negative damping shows up pretty much all over the place, but this response looks pretty good, I think, in general. Once you go to 3 milliseconds of delay, and I'm sorry, maybe it's difficult to see in the back part of the room, but you see here, at least, especially at the end of this virtual testing, it started to show a lot of high frequency stuff in there. That's the negative damping start to play a role. You are marginally unstable here. Go to 4 milliseconds as we predicted, this virtual testing goes unstable. So that's just a kind of validation saying, okay, the equation of motion we derived seems to be pretty good in predicting the system response. And the demo example 2 is another type of hybrid configuration. For example, 3-story, similar structure, and if we're only testing one column, basically, all of them modeled numerically. So conceptually, it's very easy to think about this. This system definitely is much easier to test, because now you have a predominant structure is numerically assumed, and your control error is going to be playing a less significant role in your hybrid system. And then we want to quantify it again. For example, that's the mode, 3 modes of this system again, reference structure. If I inject 1 millisecond of delay, yes, it looks like it's nearly identical. This 1 millisecond delay played very minor role in my hybrid system. Even if I go up to 10 milliseconds, you see some negative damping, but in general, it keeps up with the reference response. Even goes up to 35 milliseconds now. And now we can see that the second mode start to become nearly, marginally unstable here. Interestingly, the third mode is actually, even though it's a higher mode, it's actually more stable than the second mode in this particular configuration. So we did this system analysis, then we go back to do a virtual testing, and you see that's the reference response again. 1 millisecond of delay nearly identical from practical engineering perspective, right? Then 10 milliseconds of delay, some negative damping definitely is there. Goes up to 35 milliseconds of delay. That's when you see this negative damping make your response be much bigger than the reference response. this demo example 2 is just to give you an idea that so you depends on this type of substructure partition becomes much easier to deal with. 35 milliseconds of delay, it's easy to achieve. You don't need any fancy outer loop controller compensator. The PID will do the work. It will go do this test. Should be able to do that test. So that's about the system stability analysis. The third subtopic, I will talk a little bit about using reduced order model to do real-time hybrid simulation. So the motivation for that is, in many cases, FEA model become too complicated, the computational overhead is just too large to run in real time. But still, a lot of times we want to do a real-time hybrid simulation because your physical specimen is still having a strong presence of mass and damping. So you have to do real-time hybrid simulation. So then the way to do it is we can use a reduced order model to make it happen. What's the reduced order model? Here is just a concept illustration for structure dynamics. We see this equation of motion a lot, right? Second order differential equation. And then we can convert it into a state space formulation. Actually, it's becoming a first order first order differential equation because now your state is actually your displacement and velocity. And the time derivative of that could be expressed as a function of that state vector as well as your input vector. So in a way that if you have a higher and higher order dynamical systems, you can use a similar way to expand your state vector. Eventually you can convert it into a first order state space model. Because this state space model is widely used in the control design and the system analysis domain. If you are a system engineer, a lot of the courses will be focused on this state space type of representation. But our structure system can be converted to that straightforwardly. So this state space model, if it's a linear state space model, you can run it execute it with very low computational cost. But once you go to the FEA domain, it's not so straightforward anymore. But luckily in ANSYS, at least, there is a way to do it. For example, this is an ANSYS model, and I can just make it a very refined mesh. The point is that I can convert this FEA model into a state space model. I can define arbitrary number of input and output on this structure, and then I can construct the state space model so that this state space model, the dynamics of this space space model is the same as the dynamics of your FEA model. The first mode, second mode, all the modes are lined up with that. So using this to do a dynamical analysis will give you pretty much the same response as your FEA analysis. But using this, you can run it much faster than FEA. For example, this is one of the demo examples we run in our lab. We have a very small column dummy specimen there to testing the methodology. And this we construct an ANSYS model with only single column being tested. Everything else is model. If you want to run this model, do hybrid simulation, no way you can do real time. This model runs very slow. And then the way to do it, if we want to do a real time, we have to convert it into a state space model, then make it into Simulink, download it into our target PC, then you can actually achieve hard real time execution with 1024 Hz sampling frequency. Easy. So state space model is just much simplified in terms of computational cost. And then see a little bit about response. For example, here it shows the full model, the pure FEA model without hybrid. That's our reference solution in both X and Y direction. And then the second curve I'm showing you here is the reduced order model. That's the state space model. And that's, again, just pure analysis, no hybrid. And then we did a full model hybrid simulation using ANSYS as the driving engine, but it's a quasi-static one, because ANSYS couldn't run in real time. That's the response we got. Finally, we used a reduced order model to do hybrid simulation. Now it's a real-time hybrid simulation. You see, all the responses the major, the dynamics are captured, the response is, they correlate with each other very well. So that's just a way to do real-time hybrid simulation when you have to use some commercial FEA package, and if you still have to do real-time, then you can use this reduced order model to do it. So in summary, we give you, we use a dynamic analysis approach to get the system and level understanding about your real-time hybrid system. We derive that equation motion. We know that the hybrid system negative damping depends not only on the actuator control error, but also on the structure, substructure partition. That's a strong point I hope you can get in your mind. When you design a hybrid simulation, you can use that tool to do a first screening. So see how sensitive it is to the control error, right? And then we can also combine those with the virtual testing procedure to predict your system response. Before you go and plug in the hardware and then something happens, it's just in the blink of an eye for real-time testing. So finally, our reduced order model is an effective technique for real-time hybrid simulation implementation. Thank you. That's the end of my presentation.